All right, how's everybody doing this morning? Hanging in there? Kind of a small class, I guess. Some people are still out on vacation, huh? Hopefully people will still keep rolling in the next few minutes. All right, I'm glad that you're all here. So today we're going to start with a review of series circuits. So we talked about series circuits 2 lectures ago. So we're just going to go over those briefly, and then we'll talk about parallel resistance. We talked about that last time. And we said that this was a little bit counterintuitive. We said series circuits kind of made sense because when you got more resistors, you ended up with more resistance. Kind of stands to reason. But with parallel circuits, it was the opposite. When you got more resistors in parallel, you ended up with less overall resistance. So we'll review that. And then we'll go on to the main topic for today, which is parallel circuits with Ohm's law. So remember last time we just talked about parallel resistance, but we didn't talk about how electricity really flows through parallel circuits. So today we'll talk about how that actually works. So first of all, we'll say, why do we care, right? Why even bother learning about this stuff? And then hopefully we'll explain why it's actually important and worthwhile looking at this. Then we'll do an example of a circuit. And when we're working through this example, we'll use this fact that voltage is constant along any wire. So that's really important, and that's going to help us understand what's going on inside parallel circuits. And then we'll look at a couple of key facts for parallel circuits. Remember, in series circuits, we saw that when the current flowed out of one component, it had to flow directly into the next. There was no place else for it to go. So could the current be different from one component to another? No, exactly. In series circuits, the current was the same for all the components. But was the voltage the same? No, the voltage could change. So that's how it was in series circuits. We're going to look at the voltage and current in parallel circuits, and we're going to actually find out that it's the opposite, believe it or not. So we'll take a look at that, and then we'll go on and do a preview of today's lab. So today's lab is on page 79. Last time we did a lab that was entirely in multisim. Today our lab will be entirely hands-on. Okay? So that's the plan for today. Any questions before we get going? Okay. All right. So then let's review series circuits. Hey. So we said that in a series circuit, we had components connected end to end, almost like trains on a train track. So something like this. Okay. So we had components connected like this, and we said that the total resistance, what was the formula for the total resistance if they were all resistors?
R1 plus R2.
Yeah, exactly. So it was just R1 plus R2 plus, and then on until you got to the all of your resistors. So that was the total resistance. And then with parallel, it worked a little bit different, right? We said that in parallel components were arranged typically side by side. So it might be something like this. And so if you had 2 resistors in parallel and they were the same resistance, we could use kind of a shortcut to figure those out, right? So say they were both 1 kilo ohm resistors. What shortcut could we use to figure out that parallel resistance? Yeah, so that's the kind of the formula that works in any case, right? So if you have any resistors, you can say that R total equals, 1 over R1 plus 1 over R2, and then that can keep going for as many resistors as you like. So that'll always work. And when the resistors are the same value, though, we said that there was kind of a quicker way to do it without using that whole formula. Yeah?
You just divide one resistor by the number of resistors?
Exactly, exactly. So in this case, one resistor value is 1,000 ohms. And then we have two resistors. So the equivalent resistance up here would just be 500 ohms. Okay? And we said that the total resistance will always be less than the smallest resistor in a parallel circuit. Okay? Remember, in parallel, the more resistors you have, the less resistance you get, because it's like it's giving the electricity more paths to follow. So when you give the electricity more ways that it can flow, the resistance goes down. Okay? So that's what a parallel circuit is. This formula will always work to find parallel resistance in a parallel circuit, but sometimes you can take a shortcut when the resistor values are all the same. Okay? So any questions about that? All right. So that's parallel resistance. So then let's go on to our main topic for today, which is Ohm's law in a parallel circuit. So when we looked at Ohm's law in a series circuit, kind of the typical way to proceed was to find the equivalent resistance of the whole circuit, and then find the current for the whole circuit, and then find the voltage and current from there. And you can do kind of the same thing in a parallel circuit. So let's look at an example here. So let's say we've got a power supply, and let's say that this is 10 volts, and then we've got a resistor that is 1 kilo ohm, and another one over here that is 250 ohms. And we want to find out, call this one R1, this one R2. We want to find out basically everything about this circuit. So we want to know V total, R total, I total, and then V1, V2, I1, and I2. Okay? We want to find out all of these things. So let's see how we can do that. So first of all, is there anything we can write down here without doing any calculations?
The voltage?
Yeah, the total voltage, exactly. And what is that total voltage? 10 volts, exactly. It's the voltage that comes from the power supply. So that's 10 volts. So that's good. So then the next thing that I would do here is I would figure out the total resistance, because this is a parallel circuit, and we know how to figure out the equivalent resistance in parallel circuits, right? We just talked about that. So that's what I would do next. So we would say that R equivalent equals, can we just divide one of these by 2 resistors since we have 2 resistors here? No, yeah, because that only works when they're both the same value. So we have to use that other formula. So we say R equivalent equals 1 over 1k plus 1 over 250 ohms. Okay? So then, so let's figure these things out. So that's 1 over, and then I do 1 over 1k. So 1 over 1, that's just 1, right? No. Okay. Why not?
Make it do like kilo ohms, take it like 10 power of 3.
Right. We got kilo ohms here and not just ohms. So I have to do I have to convert that into regular ohms before I do the math. So that's 1 over 1,000 ohms plus 1 over 250 ohms. So now I can work that out. I can put it in a calculator. So what's 1 over 1,000?
0.11.
Yeah, so 0.001. Okay, and then what's 1 over 250?
0.004.
Okay, so plus 0.004. All right, so then that equals 1 over 0.001 plus 0.004 gives me 0.005. And if I do that division, what's 1 divided by 0.005?
200.
200, perfect. So that gives me 200 ohms. So that's the equivalent resistance. So that means that I can redraw this circuit with just a single resistor that is 250 ohms. And that's the R total or R equivalent. I'm sorry, 200 ohms. Misspoke. All right, so does anybody have any questions about how we got that? Okay, so then I can write that down here for my total resistance. So that's 200 ohms. So now comes the tricky part. Now we have to figure out what to do next. That's really the hardest part of these problems, is figuring out where to go. What's your next step? So anybody want to venture a suggestion about what we could work on?
I total.
Okay, yeah, we can work on I total. Perfect. And so, so how can we figure out the total current?
Ohm's law.
Yeah, Ohm's law, exactly. So let's take a look at that. So remember, Ohm's law is like this. We've got V, I, and R. So if we want to figure out 1, we write down what it is. So we want to figure out the current here. So we write down I equals, and then we cover that up, and we see that it's V over R. So in this case, what's our total voltage?
10 volts.
Perfect. And what's our total resistance? Perfect. 10 volts over 200 ohms. And so what does that give us? How much current? Okay. So 0.05. And what are the units?
Ohms.
Ampere.
Yeah, amps. Yep. So when we, and that's important, when we put in our units, our calculation, when we do our calculation with raw units, like volts and ohms, the answer comes out in raw units. So in this case, amps. So I always convert everything to raw units before I do the calculation because then I know what unit I'm going to get out. And then after you have that, then you can convert that to something else. So how many milliamps would this be? 50. Perfect. So there we go. So it's best to get your answer in raw units and then convert it afterwards so you don't get confused, okay? So now we can write that down. So we can draw it over here. We can say that we've got 50 milliamps flowing through our circuit there, and we can write that for the total current as well. So 50 milliamps, because if we have 50 milliamps flowing through that resistor, we also have 50 milliamps coming out of our power supply, and how much going back into the power supply? 50, exactly. It's always the same going out and coming back in. All right, so we got that. So that's our total current. So then if we know that that's the current flowing out of this power supply and coming back in, we know that it's got to be the same over here. So we also have 50 milliamps flowing out there and 50 milliamps going back in. All right, perfect. So then, so what's next? What could we work on next?
The voltage of the branches?
Sure. Yeah, so we can look at the voltages for these resistors. So this is where this key fact comes into play that's really important. So in any circuit that we're looking at, voltage is constant along a wire. That's a little bit of an approximation, but it works. Okay, so let me show you how that can be helpful. So remember, oftentimes we pick a point in a circuit and we call that point ground. So we'll pick this point and call that ground. And that means that we're defining that point to be 0 volts. So we can write down, we have 0 volts at that point. Now, by convention, that point is usually the negative side of the power supply, but you can really pick any point you want. Anyway, we've got 0 volts there, and we know that voltage is constant along a wire. And we've got a wire running all along the bottom of our circuit. So we've got 0 volts at this point on the wire. What's our voltage going to be at that point on the wire right there? 0 volts, because it's constant. Voltage is constant along the wire. What about over here? What's the voltage going to be at that point? What?
0 volts.
0 volts, that's right. All right, perfect. Okay, and we have our power supply over here, and that's a 10 volt power supply. That means there's a 10 volt difference from one side to the other. So we're starting at 0 volts down here, and then we're going up by 10 volts. This negative to positive, it's like going uphill. So we go up by 10 volts, we start at 0. So what's our voltage at that point up there? 10 volts, exactly. Again, that's the voltage relative to ground. That's the difference in voltage between that point and ground. So we have 10 volts up there, and the voltage is constant along a wire. So what's our voltage at that point right there? 10 volts, perfect. And what about over there? 10 volts, exactly. Anywhere along that wire, it's 10 volts. Okay, so now we can look at the voltage across our resistors. So let's look at this first one first. We've got 0 volts down here and 10 volts up there. So what is the difference between one side of that resistor and the other? 10 volts, exactly. So we have 10 volts across that resistor. What about this one over here? Also 10 volts, because we got 10 volts on the top and 0 on the bottom. 10 volts across that one. So the voltage for both of our resistors is what?
General.
10 volts, exactly. So V1 is 10 volts and V2 is 10 volts. Okay, perfect. And then let's look at the current here. So we've got, so how can we figure out the current through R1? Ohm's law, that's right, perfect. So we know the resistance and we know the voltage, so we can figure out the current. So we write down I equals V over R. And so what's our voltage across R1? 10 volts, perfect. And then our resistance here is 1 kilo ohm. I'll just translate that into 1,000 ohms. So what's 10 over 1,000? Yeah, 0.0, I think it's 0.01. Yeah, 0.01. And what are my units going to be? Amps, exactly, because I put in raw units, I get out raw units. So 0.01 amps. So that comes out to be, if I convert that to milliamps, what would that be? Yeah, 10 milliamps. All right, perfect. So that's my current through resistor 1. So I can write down here, current is 10 milliamps. So also I can draw that up here on my diagram. So I know I've got 50 milliamps right there. So that 50 milliamps is going to be flowing along here. Remember, this is like how much water is flowing through a pipe. So this is like 50 gallons per minute. And then some of it comes off and flows down through this pipe here. So down there, we said that we've got 10 milliamps. So this is like, you got 50 milliamps coming along, 10 milliamps of it goes down that way. It's like 50 gallons per minute of water, 10 gallons per minute goes down that way. So the rest of it has to go this way. So now there's two ways to figure out how much current would be flowing through R2. The first way would be to do Ohm's law again. So we could do that. We could use this resistor and the voltage and figure that out. But is there another way? Can anybody think of another way we could figure out how much current that is?
Yeah, we have total 20.
Yeah, go ahead.
Subtract 10 from 50.
Yeah, exactly. Yeah, so we got 50 here, 10 of it goes down that way, so the rest of it goes that way. So 50 minus 10 gives us 40. So we have 40 milliamps going that way. Okay? Everybody see how I got that? Okay, so in electronics, there's often more than one way to get the right answer. And so it's often helpful to learn multiple ways to do it so that you can pick the one that's best for a certain situation or that's easiest for you, okay? So in this way, in this case, we could use Ohm's law, or we could just look at the way that the current splits up, okay? And then down here at the bottom, kind of the opposite happens. So down here at the bottom, we have how much current would be flowing along this wire down here? Yeah, exactly, 40. It's the current that flows out of this resistor, so we have 40 milliamps there, and then it meets up. We got 40 down here, meets up with the 10 coming from this resistor. So then how much is flowing through that wire there? 50, exactly. And that's good because we said we better have 50 milliamps going back into our power supply up there. Okay, so that works out. So that's how we can do Ohm's law with a parallel circuit. So are there questions about that? Okay. So I just wanted to take a second to remember some things about series and parallel circuits. So we said that in series, we said that in the series circuit, the current that flows out of one component has to flow right into the next. So the current is the same for all the components. But what about the voltage? Did that have to be the same? No, the voltage could be different. Yeah, so voltage can be different. Now let's look at this parallel circuit here. What was the voltage for R1? Yep, 10 volts. And what was the voltage for R2? 10 volts. And remember, in a parallel circuit, we're always going to have this wire running along the top that has a constant voltage, and a wire running along the bottom that has a constant voltage. So really, anytime you have components between those two wires, you're going to have the same voltage across all of those components. So in a parallel circuit, the voltage is the same. So the voltage must be the same. But what about the current? Do we have the same current in R1 and R2?
No.
No. So yeah, so the current can be different. So this is kind of funny. It seems like there are several cases in electronics where you have two things that are sort of opposite, complementary almost. So with series circuit, the current is the same, but the voltage is different. In parallel, the voltage is the same, but the current is different. So they are sort of opposites of each other. Yeah.
I missed the part where you got the total current. Like,
Okay.
how did you get the total current?
Yeah, so the first thing we did is we found the total resistance, and then we knew the voltage and the resistance, so we used Ohm's law to find the current. Yep. Yeah, other questions? Okay. All right, so that's how we can analyze a parallel circuit using Ohm's law, okay? And those are the key facts that I wanted to point out about a parallel circuit, that the voltage is the same for all the components, but the current can be different, okay? So any questions about that? Should I do one more example? Are we good? Good for now? All right, cool. Well, if you have other questions later, we can take a look at that later. And we'll review it next time also. So let's go on and do a preview of today's lab. Okay, so today's lab starts on page 79 in the lab book. So the first thing that the lab book asks you to do is to build this circuit. Now I know it's really hard to see that. Let me see if we can get a better picture here. All right. Can you see that circuit on the board there? Yeah. All right. So you're going to build this circuit on a breadboard. So you can see we've got a 12-volt power supply and then 3 resistors in series. The first table asks you to measure the resistance of each resistor by itself. Now you might say, okay, well, why would I have to do that? It says I have a 7.5 kilo ohm resistor here. I'll just put down 7.5 kilo ohm. Well, don't do that, okay? The reason is because when you know that when the resistor is marked 7.5 kilo ohms, it's got a tolerance on there. So it's never going to be exactly 7.5 kilo ohms. So what we want is we want you to actually measure the real value of that resistor and then write down with as much precision as you can. So if it's 7.46 kilo ohms, write that, okay? Don't just round it to 7.5. And the reason is because when you add your resistors together, the more precise you can be, the more closely they're going to match your real circuit here. So be as precise as you can. So write down each individual resistor and then write the total resistance. And remember, when you're measuring the resistors by themselves, make sure they are out of the circuit, okay? You can't measure a resistor by itself in a circuit because you'll end up measuring the resistance of other parts of the circuit at the same time, okay? So make sure that the resistor is out of the circuit and you measure each one by itself, write down their total values and then, or their individual values, and then add them together to find the total resistance, okay? And then after you do that, actually build the circuit and connect connect everything together, and then measure the voltages across each resistor, okay? And then measure the total voltage. So that's the voltage from one side of the circuit to the other. Write that down. And then you can calculate the total current for the circuit. So what law would you use to calculate the total current here? Ohm's law, exactly, because you know the voltage and you know the resistance. So you can calculate the current there, okay? And then you can actually measure it. So down here, so you'll write down your calculated current up there, and then down here you will measure it, and hopefully your measurements come out pretty close to your calculation, okay? So, so let me just demonstrate how you can measure current in a circuit, because this is a little bit tricky sometimes. So let's say you've got your circuit set up, and you've got one resistor up there, and then one resistor here, and then one resistor down here. Okay? Now, say you wanted to measure the current through this middle resistor. Remember, what you have to do is you have to put your meter in series with that resistor in order to measure its current. So the way that I measure current through a component, remember, current is a destructive measurement. You have to partially deconstruct your circuit. So the way that I do that is if I want to measure the current through this resistor, say, what I'll do is I'll pull one leg of this resistor out of the circuit. So what I've done here is I've broken the circuit, and I've kind of created two loose ends of this circuit. And I have to hook those two loose ends of the circuit to the meter. Now, one of those loose ends should be pretty easy to see. It's this end of this resistor that's kind of hanging out in space there. The other loose end of the circuit is harder to see. That's the place where this part of the resistor used to be connected. So that's the hole where that resistor was plugged in. So what I do is I put a wire into that hole. So now hopefully it's easy to see the two loose ends of this circuit. And then to measure current, you connect each of those loose ends to one of the leads of your meter. And let's look at what this does. What happens is that the current that used to flow from this resistor straight into this resistor here and then onto the rest of the circuit now has to flow from this resistor and then up through your meter where it gets measured, and then back down here, and then it continues through this resistor and continues on through the rest of your circuit. So you're forcing that current to go through your meter and get measured. And that's what you want. That's how you measure that current, okay? So you break the circuit apart, you create these two loose ends, you connect the loose ends to your meter, you measure your current. And then after you're done with that, you put everything back the way it started. So you pull out this wire, you disconnect your meter, you plug your resistor back in where it used to be, and now you're ready to go on and make your next measurement or do whatever is next part of the lab, okay? So that's how you can measure current in a circuit. And that will always work, no matter what kind of circuit you have, whether it's a series circuit or a parallel circuit. If you want to measure current through a resistor, you just pull out one leg of that resistor, pop in a wire where that resistor used to be connected, and then hook those two loose ends of the circuit up to your meter, okay? All right, so that's how we can measure current. And that's important because that's the next part of the lab. So this part of the lab asks you to measure current through each of the resistors. And then it asks you for the total current. And remember, the total current is the current coming out of the power supply or going back into the power supply. So, so that would be, so in order to measure that, you can just break the circuit apart where the power supply connects to the circuit board, okay? So any questions about measuring current? All right.
How we measure this parallel circuit?
Okay, yeah, so the next circuit is in parallel. So you have 3 resistors in parallel like that.
We need to find I2.
Right, so you do exactly the same thing. So if you want to find the current through resistor 2 here, what you do is you pull out one leg of resistor 2, you put in a wire where resistor 2 used to be connected, and then you've got 2 loose ends of your circuit. You've got the resistor and the wire sticking out. You connect those two to the 2 leads of your meter, and you measure current that way.
Yeah. Can we do it like after like in the bottom side of the resistor?
Yes, you could do it on either side of the resistor. Either way works, it doesn't matter. Yep. Yep. So first of all, this circuit asks you to calculate your resistance. So you can use that parallel circuit formula to calculate the total resistance. And then this asks you to measure the total resistance. So the way that you measure your total resistance is, first of all, you disconnect from your power supply. That's very important. You cannot have the power supply connected. Even if it's turned off, it can't be connected at all because the power supply still has its own internal resistance even when it's turned off, and that'll affect your measurement. So your circuit has to be completely disconnected from the power supply. And then you can connect one lead of your meter to one side up here, like right there would be one lead. Your power supply is disconnected. Your other lead of your meter would go and connect right there. And then you measure the resistance between those 2 points on the circuit. And then that'll be your measured resistance for the whole circuit. Okay? So are there questions about that? All right. And then, again, you'll measure the voltage for each resistor. And then you'll measure the currents in the circuit. Okay? So you'll write down your currents up there, and then that is the end of the lab. So any questions about that? Okay. And I don't anticipate that this lab is going to take very long. So today's a good day to bring up your lab books when you're done with your lab, and I'll enter grades for all the labs that you've completed so far. Again, if you missed a day or something, or you haven't completed a homework yet, no big deal. I'll just grade what you have, and then when you make it up or you finish your homework, I'll grade that on the next time around, okay? So, yeah, so that's what we'll be doing. So any questions about the lab? Okay, then I will take attendance, and then I'll let you go.